Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. Welcome to Icon League conference. I would like to introduce myself. My name is Muhammad Hazwan Hussein. I'm currently the Associate Professor in the School of Chemical Sciences, University of Science Malaysia. And I would like to thank the organizing committee of Icon League 2022 for inviting me to this conference. And what I'm going to share with everyone today is basically my research, which we have done in several years. And the title of today's presentation is Elucidation of Oil Palm based lignin as a substitute for wood adhesive. And before we begin, I guess maybe it's best to introduce to everyone about lignocellulosic biomass. And we know that this biomass is actually derived from living or recently living organisms, and it could be coming from plants and plant-based materials. And some statistics have shown that lignocellulosic biomass actually occupies more than half of ocean and land. So that's actually show how much this biomass waste been produced throughout the year. And then it has been said that this biomass could be one of the promising source of renewable energy. And looking at the name itself, lignocellulosic biomass, we know that the main component of this biomass is actually cellulose, around 30 to 50%, hemicellulose 20 to 30, and followed by lignin around 10 to 30%. The current trends of utilizing lignocellulosic biomass into fuels or chemicals have been largely studied, and this could be done by employing thermal and chemical or biochemical methods. Therefore, the main concept in biorefineries is basically when you have lignocellulosic biomass, it will be first treated in a primary biorefinery. So this pretreatment is actually important to separate the major component of lignocellulosic biomass. You can have cellulose, hemicellulose, lignin, and then after that, the secondary biorefinery actually refine all these components into a more refined structure, such as furfural, vanillin, and whatsoever. And these refined chemicals can be used for further applications. And the work that we have done quite recently is more focused on the oil palm biomass. We know that Indonesia, Malaysia are actually the highest contributor of palm oil products. And for Malaysia alone, due to massive activities in palm oil industries, it actually generates around 50 million tons of lignocellulosic biomass waste every year. And from this oil palm biomass, we can actually categorize it according to their parts. So you can have anti-fruit bunches. After they press, they actually discard the bunches, the empty bunches. And this actually around 4 million tons per year. And we also have oil palm fronds, which normally prune during the plantation. And then the degeneration of OPF is around 24 million tons per year, quite high as compared to the other types of biomass, which is actually oil palm trunk, which normally around 3 million tons per year. So our work normally focus on OPF, but we also tried with other oil palm biomass waste as well. But as I said, I think the work that I'm going to share today is more or less related to OPF. And to separate the major component, as I said, we need to do the pre-treatment. So some basics of the delignification process need to be understood. The purpose of delignification process, or some people call it as pulping process, is actually to separate the components of wood into lignin, hemicellulose, and cellulose. This technique has been largely used in paper industries. In Scandinavian countries, they are using pulping methods in order to produce pulp and paper. And the resultant product are actually pulp and also black liquor. So the black liquor actually very rich with lignin and hemicellulose, meanwhile the pulp is actually very rich with cellulose. The delignification process can be done using high pressure and high temperature reactors with the addition of some chemicals like alkaline and some organic solvents with a known solid to liquid ratio. And some basics of pulping process, we have I think alkaline process and organosoft process. So for craft process, the types of chemical used is basically sodium hydroxide and also sodium sulfide. And this chemical actually produce I think sulfide functionalities into the craft lignin. The working temperature is around 150 to 180, and time is around 1 to 3 hours. So it's quite a severe process. Meanwhile, for soda process, it's almost the same, except that the types of chemical used in this case is only sodium hydroxide. Working temperature and time is almost the same, and this actually could produce around 20 to 30% of lignin yield extractive after the process. And finally, we also did some organosoft process. And in organosoft process, what basically we are going to use, a mixture between organic solvent, which in this case we are using ethanol mixed with a certain percentage of water in the presence of a small amount of organic acid and or mineral acid. And then what happened is that the temperature is slightly increased around 150 to 190 with a working temperature quite a short time, around half an hour to 2 hours. The comparison between the pulping process, maybe you might wonder what's the difference between the quality of the lignin obtained. Obviously, when you extract the lignin using alkaline process, you obtain more condensed structure as compared to the one that is isolated using organosoft method. So the organosoft method produces a lower amount or yield of lignin, but it gives a slightly better properties in terms of the solubility or antioxidant activity rather than alkaline process lignin. And talking about lignin, maybe some of you don't have any idea what is actually lignin. So lignin is actually a polyphenolic compound composed of major phenylflavonoid monomers, paracomeric alcohol, guaiac alcohol, and stringent alcohol. So it's actually considered as a waste product of pulping and bleaching process. Lignin is actually not toxic, complex in nature, and it is actually natural phenolic polymer. And some recent studies have shown that there's an increase in potency in many applications, such as the use of lignin as a binder, dispersant, emulsifier, corrosion inhibitors, antioxidant, and whatnot. The work is actually more focused on wood adhesive. We know that the common types of wood adhesive available in the market is actually formaldehyde-based wood adhesive. You can have phenol formaldehyde, urea formaldehyde, melamine urea formaldehyde, and whatsoever. So urea is considered to be the raw materials in resin production. This is because it has these aldehyde functionalities, but certain exposure of formaldehyde into human can cause several threats, because we know that this type of chemical is actually carcinogen. At certain limit, it can actually cause irritation to human, and even it can cause cancer. So some other alternatives that we did in the current study was to replace formaldehyde with a less toxic aldehyde, which in this case glycoside. So glycoside is actually the dialdehyde. So function as the same, to produce a cross-linking with the phenolic material, but it gives a more safer, properties as compared to formaldehyde. The basics of resinification process for lignin-based adhesive, we consider lignin as the substitutes to phenol, because all the time phenols are coming from petroleum-based industries. Sooner or later, there will be a depletion of these chemicals. Therefore, what we have proposed as well is actually to replace phenols with lignin. and at the same time replacing formaldehyde with glycol. So in the end of the day, we are producing a more green, less toxic wood adhesive. The basic concept of resinification is the same. You have a active reaction sites in lignin structure, mainly for guasil and also for H functionalities. Then all this condensation or the formation of methylene bridge can be formed. People have studied lignin-based wood adhesive, I think, in many years. And what they did was they tried to isolate lignin from different biomass, and then they formulate it into a different wood adhesive. So depending on the types of lignin that they obtain from different biomass, it will give different properties in terms of mechanical properties. And I think so far there's a lack of study that actually use dialdehyde or glycol in replacement to formaldehyde. Therefore, in our studies, what we did was we isolate the lignin from oil palm biomass, which in this case more specifically on oil palm fronds. And then the oil palm fronds basically was cut into small pieces, and then it will be grind. And after that, the ground OPF powder will be subjected into pulping reactor. So we did different kinds of pulping process, but in this case, we are actually focused more on craft and also organosoft lignin. Meanwhile, after we obtain the black liquor, we precipitate it, and then we obtain lignin. We characterize it using a normal physical-chemical characterization, and we also did the resinification process. So the resinification that we did in our study is actually by substituting different percentage of lignin with phenol, and at the same time, we replace entirely formaldehyde with glycol. So certain percentage of the 10, 30, and 50 substitution, lignin substitution be used. And we are also using some small amount of catalyst, base catalyst, and also the solvent that we use is actually ethanol. And some might wonder why we use ethanol, because using ethanol as compared with water, it actually provides faster curing as compared to water. So that's basically the main reason why we replace it with ethanol. So after we obtain the resin, what we did was we concentrate it, and then we apply it on the plywood. Okay, so it's a 3-layer plywood following a standards. And then after that, it will be cured using hot press, and it will be cut into a different dimension. This is also following a standard ASTM standards and subjected to UTM machine, universal tensile machine, to study the tensile properties, modulus of elasticities, and internal bonding. So the wood adhesive properties that we have studied, actually we look at the solid content, viscosity, gel time, and also pH. And as we increase the lignin substitution, we observe that the viscosity actually increase, gel time become faster, and also the solid content become higher. So this is actually in a good agreement with other findings as well. And surprisingly, what we have obtained was 50% of organosoft lignin phenol glycol produce higher solid content, higher viscosity, and also a shorter gel time. So the resin was further characterized using some complementary analysis. For example, using FTIR. So what we have determined over here was the formation of a methylene bridge. So it means that the cross-linking process actually successful, and this actually supports that the formation of cross-linking bridge depends entirely with the content of HGS ratio. And the other thing was we also characterize it using carbon NMR. So from the carbon NMR, we also detected the methylene link, cross-linking bridge, as well as other functionalities with regards to methyl groups and other things. We also proceed with a thermal analysis. So from the thermal analysis, what happened was, as we increased the percentage of lignin substitution, the delta T, the change of temperature, is actually decreasing. So lower value of delta T indicates higher rates of curing of resin. It means that the curing will become faster. And it so happens that 50% of organosoft lignin phenol glycol produce the lower delta T values. And finally, we did mechanical properties. So the panels was actually tested, and we actually did for dry condition and wet condition. For dry condition, we observed that 50% of all organosoft lignin phenol glycol produce higher tensile as compared to the other percentage and also the control. Meanwhile, in the wet condition, so wet condition means that the panels soak in the boiling water and in the several hours, and then after that we dry it and subject it to mechanical properties. So even though some percentage show some delamination, but 50% of organosoft lignin phenol glycol still shows a better tensile properties. And we also did some comparative study between 50% of organosoft lignin phenol glycol with a commercial PF resin. So what happened was it showed some tremendous increase in, for the lignin that adhesive that we have developed as compared to commercial PF. So it means that it's still acceptable to be used in industrial application. So as a conclusion, what we have found out was smaller fragments of lignin obtained from the organosoft pulping process produce a higher phenolic OH content, and this higher phenolic content actually contributes to more reactive sites for the cross-linking to happen. And the higher mechanical strength of 50% of organosoft lignin phenol glycol was probably due to a more cross-linking, as I said earlier, because of higher phenolic content. For organosoft lignin phenol glycol resin structure. So to end, I would like to acknowledge my university, University of Science Malaysia, for providing research grant, and also our contributor, our collaborator in this study, majorly coming from France, Université de Lorraine, Professor Nicolas, Isabelle, Laurent, and also Francois. And some other collaboration with BRIN, named researcher Dr. Widya, Dr. Firda, and also Dr. Adli. We actually published some review articles together. And I would like to acknowledge my students as well, who've been working a lot in developing the wood adhesive from all biomass waste. So with that, thank you very much for your attention, and I'm happy to answer any of your questions. Thank you and terima kasih.